recording. All right, so today we're actually going to start talking about all the types of radioactivity. Starts with I put myself up there. Starts with neutron-proton ratio. The neutron-proton ratio is extremely, extremely key in this. There's a couple of rules, and this is where if you want to take the AP exam, this is where they ask a lot of questions about it. What things are stable, what things are unstable, because that's where you want to get. That's what the neutron-proton ratio is for. First off, everything above element 84 is unstable. That means they are radioactive, okay? Anything above 84 on the periodic table, the atomic number is radioactive, okay? So, and you kind of know that. You know that the actinides are all radioactive, and that's 89. And that's a property of them. So 84 and above, all radioactive. And those are the ones we're going to deal with most. Now, does that mean that other elements are not radioactive? No, okay? Everything is radioactive. But if you can look on your periodic table, did I not give you on your periodic tables? You did. Okay, let me borrow one of your periodic tables. If you look on your periodic table, you're going to notice that on the back of it, it is going to give you somewhere the half-life, okay, and then the longest lived the half-life. So that's how long it takes half of the decompose. We're going to talk about that in this unit, okay? So half-life exactly is how long it's going to take for half of it to go away, and then the longest lived isotope. So you can look at carbon. It tells you that carbon's longest half-life is 5,730 years. So you think you're going to be dealing with much chemistry that's talking about the half-life of carbon? No, but that's why carbon dating is so efficient, okay? Because it takes 5,000 years for half of carbon to go away. And then it also gives you the most stable, or which one lives the longest, so which one gave you that isotope, so carbon-14 gives you that. Now you can see some are in years, some of them are like in feroseconds, okay? Look down at californium and berkelium. I think those are in feroseconds, so their half-life is like nothing. I mean, that's 10?
No, 10? California?
Has an E in it.
California? This half-life is
No, the element 10, Tin.
Oh, that's that E means times 10 to the 50. So that is 10,000 years. So 100,000 years. It's 100,000 years. That's basically what it is.
Wait, what do you explain?
It says 1.0 whatever E5. Okay, so that E means.
So you said look where?
But
And then it says.
No, I'm looking at that. Which did you say? Kingston?
California and Berkeley. Oh, those are years. I'm sorry.
No,
The
you
shortest
covered
ones
your
are
nose.
feroseconds. The shortest ones are feroseconds. That's the longest one. Milliseconds there. Some of the shortest ones are in feroseconds, so it's super, super tight. Those are the longest lived isotopes, okay? Light nuclei, now here's the hard thing. There is no hard and fast rule what's a light and what's a heavy, okay? So there's not like, oh, the first 50 are light, the first, 51 to whatever is heavy. There's really no rule on that. But, light nuclei are stable when neutron-proton ratio is 1. And you see this very often. Oxygen 16 is stable, okay? First off, look at oxygen. What is the, I really need to get the table up. What is the isotope that they're talking about in oxygen? 15, okay? Yeah, longest lived isotope. So that's kind of the most stable one, okay? And you notice that its neutron-proton ratio is 1, and actually neutron-proton ratio, it's all those are really close to 1. It has 7 protons, 8 protons, 7 neutrons, oxygen 16, 8, and 8. So you'll notice that even carbon-12 is the most common form of carbon, isn't it? Its proton-neutron ratio is 1, okay?
How do you know that?
Because carbon-12 tells you that its mass number is 12. We know carbon has 6 protons. So mass number minus protons gives you number of neutrons. Mass number minus protons gives you neutrons. Heavier ones, you're going to notice your heavier ones, like lead. Lead's where pretty much everything stops. Lead 206 where everything stops. So that gives you, lead has 82 protons, lead 206 gives you 124 neutrons. So that is a heavier, that's heavier, and that's why you see that it's more stable when it's greater than 1. Okay.
So the heavier ones have more neutrons.
Yes, the heavier ones have more, compared to have more neutrons. Yes, that's
What makes it heavy?
how many protons and neutrons it has. And the heavier ones have more neutrons. They want that. Why is my thing not wanting to go? Alrighty, now these are just weird things. I mean, I think this is very weird, but even numbers are more stable than odd numbers. Don't ask me why, I don't know the answer. But I'm just telling you that they're even's more stable than odd. I would assume that's because they pair up. Don't really know, but even's more stable than odd. Certain numbers are especially stable. 2, 8, 20, 58, or 2, 20, 2, 8, 20, 28, 50, 82, and 126. This is either protons or neutrons, okay, of this. The stable ones of those numbers are either protons or neutrons. And how, I remember 82 being stable for one reason. That's lead. And you're going to find out that lead is where stuff stops most of the time, okay? Don't ask me why, and you'll notice all those aren't even numbers, aren't they? That's where everything above 84 is radioactive. But everything stops at lead 206. At lead 206. Don't ask me why. Too many protons will cause by positron. We'll talk about what positron is today. Too many neutrons will cause beta particle production, okay? And that's where we are. So there are particles of radioactivity. We just talked about two things, beta and positron. We'll also have an alpha particle. That's the Greek letter A, okay? That's the Greek letter A, or the Greek letter alpha. It is a helium. A alpha particle is a helium. It is low energy. I can write this another way, and I'm sorry for people that aren't here to see this, but I can write this as an alpha particle is written very commonly as 4,2-He, okay? Very commonly written as 4,2-He. I do it because it's a whole lot easier for me to type in He than it is for me to go find alpha, okay? So it's a 4,2-He, and it's a helium nucleus. Now, what does everyone know about helium? What do you know about helium? What? Okay, well, what else do you know about it? You're both correct. We're running out of it. We're running out of it. That, because we're using it for so much stuff. There's a lot of, it's in some lasers, we put it in balloons. There's a lot of things we use helium for, but we're running out of it. This is not making more helium. Because the key word there, this is a helium nucleus. There are no electrons in this, okay? There are no electrons. It's only the protons and neutrons, okay?
Helium doesn't reproduce over time.
Yeah, supernova.
I mean, it does, but not anywhere at the rate we're using it. Okay, we are using, it's like even helium now, when you go buy helium, like a helium balloon, you're not getting pure helium. Like used to, when I was little, a helium balloon would last weeks. Now, at that first day, it's starting to sag and do stuff like that. Yeah.
So why do they still use helium?
Because people want them to float. There's nothing else we can find that's that easy, that's lighter than air. That's less dense than air. That's why it floats. But it is a relatively low energy, okay? Other thing is a beta particle. A beta particle, that's the Greek letter beta, okay? It's kind of like a B. It is an electron. It is medium energy. It can be written another way. Beta particle could be written as an electron. It is 0, -1, E. Okay, that is how we symbolically write an electron. It has no mass. An electron relatively has a 0 mass, and it has a negative charge. Okay, the mass of helium, an alpha particle, is 4, and it has a charge of +2. It has 2 protons. So it is medium energy. Gamma ray is a photon. Okay, it is a photon. It has no mass or no energy. It can be written. I can't really write a gamma ray. I just write Y, 0, 0. No mass, no charge. Okay, no protons, no neutrons. It is nothing but energy. It's a photon. Okay, It is a photon. You also have a positron. Okay, a positron is a positive electron. Okay, it's the same thing as electron. It's a positive electron. That's what a positron is. No, it is a, and then we talked about that in the last slide. Things with too many protons, if the proton-neutron ratio is too light, or I mean, if the neutron-proton is too low, positron production will occur. It's going to
Why do you have a positive electron and not just one proton?
because a proton has mass. Okay, an electron doesn't. Okay, so you can think of it like a proton, but without any mass.
Well, what makes the difference in a proton having mass and a positron?
The charge.
They're both positive.
It's like a positive electron. I know it's very difficult to think of.
It's
Don't overthink it. It's just a
positive negative.
It's a positive electron. It's the antiparticle of it. So I can write a positron, okay, as 0, 1 e. Okay, 0, 1 e. That's the positive electron. It has no mass, but it has a positive charge. Those are our only 4 types of radioactive particles. Okay. When you're seeing people getting like sunburned and getting, I'm being dumb right now. Yeah, whatever that's called, melanoma, it's because they're getting too many gamma rays. Okay, they're getting too many gamma rays. It's typically what that's occurring from the sun.
So what's the next one?
It's different. It's a different wavelength. Okay. All right. Types of radioactive decay, 6 types. We're going to talk about each one of them. Alpha particle production. As a production, we're going to produce an alpha particle. Beta particle production. We're going to have a beta particle in the products. Why did that stop? I have no idea what just happened. There we go. That's gamma ray production. That's in the products. Positron production. Electron capture, that's going to be the electron in the reactants, and then finally fission. Okay, this is finally fission. Fission is the breaking part of an atom. Important things about this. This is a huge important slide. Each radioactive decay, mass numbers is constant. You balance by mass numbers. You balance by atomic numbers. Okay, this makes sense when we start looking at one here in a second. Okay, so alpha particle production. That means a nucleus loses an alpha particle. It's common for heavy nuclides. An example of this is that, okay?
What?
That is what a nuclear reaction looks like, okay? Now, it's an alpha particle production. So I made my alpha particle, didn't I? I could have written that as helium instead of the A, all right? And go ahead. Okay, so the top number is the mass number. The bottom number is the atomic number. Remember, the atomic number determines the element. So you can see that the mass numbers are equal. 239 equals 235 plus 4. That's correct. 94, that's plutonium, I believe. I could be wrong with that. I lose an alpha particle, so I know that I'm what number plus 2 equals 94 is 92, and it becomes uranium because uranium is element number 92. That makes sense to you.
Yeah, right.
No. It'll be in there. You can look at it later.
I mean, we have to like write equations.
Yes, you have to write equations like that. It's not as bad as you think. It's not as bad as you think. All right. So that just explained it. Okay. Losing protons changes identity element. But atomic number determines the element. All right. Beta particle. We're going to go through and we're going to give some more examples once we get through them all. Okay. So beta particle production. Which thing am I making? This thing. Okay. So I'm going to produce that. So a nucleus emits an electron. It doesn't contain electrons. What it does, it is a neutron is converted to a proton. Why is this not move? Well, this guy just says released by the nucleus. Okay, it says released by the nucleus. So this is what happens. Okay, a neutron is converted to a proton. And because it's converted to a proton, that is where your beta particle comes from, okay? Now notice, are my mass numbers equal in there? What's the sum? 1 equals 1 plus 0 is my atomic number equal. 0 equals 1 minus 1, correct? So that is where we get that from. So that's, I already have that. I'll beat you to it. So the beta is written by an electron. So example of this. Okay. It happens when the neutron-proton ratio is too high, too many neutrons. So here we go. It will tell you strontium undergoes beta decay is how the question is going to be working. Okay. So strontium 90. So I write strontium 90 symbolically. Now, why is it a 38? Atomic number of strontium. Okay. So here I've got, does the mass number in beta decay change? No, because 90 equals 90 plus 0. Okay. And now notice 38 equals 39 minus 1. The big thing is the hardest thing to do is to remember what each particle is. Know that a beta, know that that's beta. Know that a beta is an electron. Know that an alpha is a 4,2 He. Okay, that's the hardest thing to do. Know that a positron is 0,1 E. Okay.
So alpha's
Alpha is always 4,2 He. Uh-huh.
So
Beta is always an electron.
that's exactly what we plug in for beta no matter what.
Every time.
Every
I mean, you could write it as an E. I would write it as an E personally, but say it's potato, potato.
You just have to make the other two work.
And it would tell you what the first thing is. It'll tell you, like today, I'll pull up your homework too. I'll put that up here in a little bit and show you what it is. But it's going to tell you what to do. So you just have to pick out the other particles. Pretty much all you're doing is filling in the blanks. Okay. You know what you start with. You know one of the things you end up with. So you have to be able to find the other thing. So there we go. I've already went over that. Products are an electron, same mass, but more proton. Adding a proton changes the identity of it. Gamma ray production is the easiest one ever. What's the mass of a gamma particle? What's the atomic number of a gamma particle? 0. So does anything change other than you writing 0, 0, Y? Nope. Okay. It releases energy. It frequently, yeah, that's the big thing. It frequently occurs with other types of decay. Mouse. Frequently occurs with other types of decay. You only have to write gamma when it specifically asks for gamma. Okay. Gamma occurs with beta. Gamma occurs with alpha. But wait, you only have to write it when it specifically asks for it. So here's a gamma. I'm going to tell you that uranium-238 undergoes gamma decay or gamma production. Other than you write the same thing plus 0, 0, Y. It's the same thing. Okay. Only when it's specifically asked for. Okay. Because gamma occurs all the time, almost all the time. Okay. So and it's a particle, so we're going through them all. So like I have my example here. It's telling you that when uranium-238 undergoes alpha decay, it's also in there. But you only have to put it in there when it specifically asks for gamma. It's kind of always there. It's kind of like when we started talking about balancing last year. When I made you balance, I made you write 1 when we first started in front of things because just re-emphasize the fact that it's there. Kind of same thing to do with gamma. As you go along, you do things unless it specifically asks for gamma. Unless I specifically ask what's the coefficient in front of something, you don't need it. But you know that it's there.
So we have to write gamma.
No, only unless it's specifically asked for. And one of your sections today of your homework specifically asked for it. So guess what? That's the easiest section to do with your homework. All right, positron production. That's a positive electron. Now here's the thing. There is no positron that exists in the nucleus, okay? It's produced by energy being released in the nucleus. A proton is converted to a neutron. Okay, so this is kind of the opposite thing of beta, isn't it? You saw in beta, where's my mouse? You saw in beta that a neutron was converted to a proton, okay? Here are the other things happening. A proton is converted to a neutron. Is this still balanced? Still balanced. And that's the way to write a proton. 1,1p plus or 1,1p. There's your neutron 1,0 in. All right, so it happens with the neutron rate too low. So here's our example of it. Tell you sodium under 22 undergoes positron production. So I wrote my formula for my nuclear symbol for sodium 22. I wrote my positron, and now notice it's the opposite of beta. In beta, the atomic number increased for our new thing. In positron, our atomic number decreased because we just have to balance it. Okay, we just have to balance it. This is going to become a lot easier when we start doing problems of it. Moves a proton. Now, if a electron and a positron meet, guess what? It's bad news. When they made the Hadron Collider, they were talking about that, and they were talking about maybe forming a black hole. This was the process they were using. Thankfully, it didn't happen. It was able to absorb enough energy not to create a black hole. Okay? That to check to test stuff like this.
Wait, so if they got it wrong, why would they? That's wrong.
Science.
I don't want to doctor the science.
That's science. I mean, now thankfully there was enough energy there, and it was in an enclosed space. But there, I mean, that there was a chance that it was going to happen. So that's not good news.
Where did they make that at?
Sweden. I think Sweden or Switzerland. I can't remember which one.
Oh, it's Switzerland.
It's one of those two. All right. Electron capture. You tells you exactly what it does. It captures electron. This is the only one where the thing is in the reactants. Okay. Now notice the gamma rays are in there. Unless it's specifically asked for it, you don't have to worry about putting it. My mass numbers are still balanced. My atomic numbers, 80 minus 1 is still 79. All right, last one we're talking about is fission. Okay, fissions. Fission is the splitting of a nucleus into lighter nuclei. Now, fission is probably the hardest one to do, but the easiest one to do. Okay, there's more than, for the purposes of this class, there's more than one correct answer. Okay, the only thing you need to make sure you do is you balance the mass numbers and balance the atomic numbers. Okay, we'll work some examples of these too. Here's an example. Now notice neutrons occur a lot in this, okay? You have to have, I'm about to put, if I can move this. So this is where people get a little confused with this, okay? What is the mass number of my of my reactants? $236. That's 1 plus 235. Now, taking out this 310 in, my mass number is only 233, correct? So I had it, so I've got to balance it some way. So then I can go ahead and add 3 neutrons into it, okay? Now, in this one, you would distribute that 3 to here. So when you do fission, the only rule you have to have is the mass number, or you have 2 rules. The mass numbers and atomic numbers have to balance, but you have to pick correct isotopes, okay? You can't end something up with oxygen 20, because does oxygen 20 exist? No. You have to end up with an actual isotope of the element, okay? So, let me stop presenting this screen and pull up the paint. So, nuclear lighter, good stuff in there. The nucleus is split. That's where we're going to stop today, okay? We're going to work some examples of this, and I'm going to tell you what we need to do. So let me pull up my paint. Did y'all like my paint yesterday? Didn't I write so neat? I'm so proud of myself.
It was so slow, I had to speed it up.
Actually, let me see if I
Oh, yeah.
let me see if I have one in here. Okay. What? Yes. There's so much energy. That the mass defect. We talked about that yesterday. The mass defects, then there's a lot of bonding energy because the mass is smaller than it should have been. Let me find. My computer is getting super slow. Probably because I have like 87,000 things open. What? I didn't hear you, Seth. I wasn't listening.
What makes it split when it gets to the ground?
What?
Like the bomb.
There's it's something in there there's stuff that's already in there. I have like 1,000 of these things. Come on, slow computer. That's the same worksheet that I'm trying to give us homework. So close that one out. Not so much for members homework. Why is my computer being so stinking slow? Well, I guess that we're going to. I'll just come. So let's say that, well, I'll just pull up Paint. So I think the easiest thing to do in hindsight. Paint. Why are you not working? Paint. All right, so let me change the screen I'm sharing. So we're going to say that I want uranium-236 to go undergo alpha decay. So uranium (236) alpha. Did this yesterday, Seth? We're behind there, buddy. What? Why not do it? Well, my mouse is being really dumb today. They sprayed that stuff on the. They sprayed the stuff very sticky that they sprayed yesterday. Okay, alpha decay. People that are at home, you listen to that. Alpha decay. So now we need uranium. The question is for uranium-236 to go undergo alpha decay. All right, so I need to start with my nuclear symbol, okay? So how would I write uranium-236 into an equation? The mass number goes to the top, so 2. Two 36. This is way too big. Actually, let me do it. Let me stop doing something else. We're gonna go to the board. We're gonna go to the board. So Zoom people, we're going to the board. So uranium-236 is undergoing alpha decay. So uranium-236 undergoes alpha decay. So I need to write my nuclear symbol of uranium-236 first, okay? So that's 236 U-92. Undergoes alpha decay, so no, that's going to be my only thing in my reactants, correct?
Are they always giving you a math number?
Yes. Well, it might ask you, what's the mass number of the original nuclide if it undergoes alpha decay and makes some whatever else, okay? You might have to fill in that blank, okay? But if you got everything else. So, what's my first reactant going to be? Alpha decay. So what's my first reactant going to be? What? Well, my first reactant would make life easier. It doesn't really matter which one you go with first. 4,2-HE. Plus, so what my mass number of my other nuclide have to be? 232. What about my atomic number? 90. And what element would that be, Seth? Thorium. TH, Brett?
Where did you get 4 to?
Alpha decay.
Okay.
Alpha particle. Let's say, okay, now let's say that bismuth 206
Teachers, please dismiss the football players to the field house at this time.
undergoes
Please dismiss all football
beta
players to the field house
decay.
at this time.
Bismuth 206 undergoes beta decay. So I need to write my first nuclide first, correct? So that would be 206 Bi, and what's Bi? 83? Right next to lead. I think it's 83. Could be 84.
83.
83 is what I thought. All right, so that's the only thing I've got here. So I've got my arrow now. And what's my radioactive particle? So what's that going to be? 0, -1.
Is it E or B?
Doesn't matter. I write E. I can't write the beta symbol. And then plus, what's the mass number of my other thing have to be? 206. Atomic number? 84. This is where most people make that same mistake because the negative is going to increase. And 84 is polonium. That's it. Okay. That's now I could have done electron capture. Okay. I could have done positron, but it's still the same stuff. Okay. Start with your nuclei and just do what you have to do. Just balance your mass numbers. Not as bad as it looked originally, is it? But let's do a fission one. Okay. Let's do a fission. Because fission can, in some ways, can be the easiest, but it can also be the hardest. So let's say that, I like to pick different elements. Let's say that PA 231 undergoes fission. So I need to write my nuclide of that. So it's 231 PA, and what's it, 90? 91? Yields. This is where I can tell if you cheat when we do fission for the purposes of this class. Because everybody can probably have many different ways. All you need to do is have your atomic number add up to be 91 and your mass numbers add up to be 231. So no matter which elements you pick, no, I'm probably not going to pick something big and small, okay? I'm probably going to try to pick something kind of in the middle, okay? So on this one, I'm probably going to pick 45 and 40 elements, 45 and elements 46, okay? Because they had 91. I could have picked 40, 41, and 50. Probably would have been a better one to pick 41 and 50 because we know that 50 is very stable, okay? So we'll go with 41 and 50. So 50 is 10 plus 41. What's element 41?
Niobidium.
NB.
NB.
All right, so now here's kind of the only other requirement. My atomic number is balance, okay? What are some values, what are some isotopes of 10? If you're unsure, you can always look at your periodic table. It tells you somewhere. Actually, no, it doesn't. But well, it gives you the most stable abundant isotope and longest lived isotope. Okay, so you got to just pick an isotope. So you can typically try to pick something around its average atomic mass, can't you? So what's the average atomic mass of 10? So you can probably pick 118, couldn't you? So I'm gonna put 118 up there. What about nobelinium? I think it's niobium. 93. Well, that one worked out really well. I did a good job picking. Are my mass numbers balanced? Is 118 plus 93 equal to 231? No. I'm how many short? 10. 10 short. So you know what I do? Plus 10 neutrons. So 10, 1, or 10, 1, 0. Yeah. That's it. That's the only thing that's kind of hard about fission is you got to add a lot of extra neutrons in there when you're done most of the time, okay?
So do you always go by the average?
You don't have to. I mean, if I would,
Every time?
yeah, just round it. I mean, they wouldn't take off. Like the AP exam doesn't expect you to know.
So like if I would have rounded 118 to 119 because there's a 7 after the 8,
Yeah, I mean, then
I only had plus 9.
Yeah.
Okay.
Same thing. That's what I'm saying. That's how I can tell if you cheat. If y'all come up with the exact same things with fission ones, well, nobody probably thinks the same way. I would use 45 and 46, but 50 was probably a better option because 50 is one of those numbers that were stable. Okay.
So you want to use more stable numbers?
And you want, like I say, you want to try to use even numbers. Now I know I couldn't get an even. That's probably why I probably use 118 also, because that would have given me stable there. But there's no right or wrong answer. All we're looking at is that you split it into two smaller things, okay, and that then when you're finished, you split into smaller things with those isotopes that do exist, and then the mass and atomic numbers balance. So that's it today.
I have questions too.
More.